Boolean algebra is the branch of algebra in which the values of the variables are truth values, true and false, usually denoted by 1 and 0. It was introduced by George Boole in 1847. Boolean algebra is widely used development of digital electronics in system and is not just applied to digital system but also used the circumstance. In fact, it can be played with any system. For example, on and off, open close, true or false, and etc. Now, since the digital circuit is offered in two signals, we can apply Boolean algebra concept and rules and laws to derive the equation with locking the equation.
Hi everyone, today I'm going to discuss some introduction of Boolean algebra. So we're going to start with the NOT, AND, and OR gates. So like a first reporter said, Boolean algebra uses 1 and 0 to represent data. So 0 can be considered as false or off, while 1 can be considered as true or on. So let's start with the NOT gate. The NOT gate is represented like this. A triangle with a small circle at its end. We're gonna use A for the input and Q for the output. So when we put in a 0, the output we get is 1. So if we put 1, the output we will get is 0. So the NOT gate is also called as the inversion, or it's also called as inverter because it switches whatever the input you put, it gives you the opposite output. So when we write this in Boolean expression, it will be Q is equal to A NOT. So the bar over the A means the inversion of A or the opposite of A. Next is the AND gate. An AND gate takes 2 or more inputs. In my example here, there is only 2 inputs. A and B gives one output which we'll use Q to refer as the output. So when we put 2 zeros, the output would be 0. Why? Because 0 and 0 is 0. The only way we're going to get a positive output from this is if we put 2 ones So, like what I said earlier, the only way we're going to get a positive output from this is if we input 2 ones. So if we input 0 and 1, we still get 0. One and 0, we will still get a 0. So the only way we get 1 out of Q output is if we put 1 for A and B for the input. So when we write this in Boolean expression, it will be Q is equal to A dot B or A times B or AB. You can also have 3 inputs as what I said earlier for a AND gate, and it works the same way. If you have all 3 ones, you will get a 1 output. But if any of the inputs is a 0, then the output will be 0. Next is the OR gate. An OR gate can have 2 or more inputs. In my example here, there is only 2 inputs, A and B, and 1 output, which we'll refer as Q. So when we put 2 zeros, we get 0 output. Remember that Q will be positive or 1 whenever either A or B is 1. So 0 and 1 will get 1. 1 and 0 will still get 1. 1 and 1 will still get 1. Again, 1 and 0 will give us a 1 output, and 1 and 1 will give us 1 output. So when we write this in Boolean expression, it will be Q is equal to A plus B. So the plus means OR. So when you read this, Q is equal to A or B. Again, like the OR and AND, it can have 3 inputs or more. So 0, 1, 1 will give us 1. As long as any of this input is 1, the output will be a 1. So if we input 1, 0, 0, we will still get a 1 output. Only when 3 inputs are 0, when we get a 0 output.
So we'll start from the NAND gate. So NAND gate takes 2 input, we'll call those A and B, and use of output, we'll call it Q. As you can see, NAND gate looks very similar to AND gate, except it has an additional circle around the end of it, which inverts the output. So NAND gate is equivalent to a NOT gate placed in front of an AND gate. This is the standard AND operation, and the output is inverted. So in terms of algebraic notations, Q or output is equal to A dot B, which means A and B, and then the bar over it, which means NOT or the inversion of that. So we'll cycle through the different inputs and show the truth table, which shows you what output you'll get for each input. So we have here an input of 0 for A and B, and this will result to 1 for the output. When we give 0 and 1 input, we'll get 1 output. If 1 and 0, the output is still 1. Only when we have both 1 for inputs, we'll get a 0 for the output. So this is the NAND operation. So let me show you how that compares to the AND operation. You can see it's exactly the opposite. The NOT gate out in front of the AND gate operation is just inverting the output. So this is the NAND operation, and this one is the AND operation. You only get 1 output if both inputs are 1. All the other outputs are zeros, and the NAND operation gives you the exact inverse of that. Next is the NOR gate. NOR is basically NOT combined with OR. So it accepts 2 or more inputs. We'll call those A and B, and Q for the output. The symbol for the NOR gate is similar to the OR gate, but it also has a little circle placed in front, which inverts the output just like the NAND gate. You can see functionally this is equivalent to the OR gate with an inverted place down in front of it. So the algebraic notation Q, the output, is equal to the input A or B inverted. So this is called A nor B. So if we have the 0, 0 input, the output is 1. If 0 and 1 input, we'll get a 0 output. 1, 0 input, the output is 0. 1, 1 input, we'll get a 0 output. We'll only get a positive output when we have 2 zeros in input. This is exactly the inverse of the OR gate, as you can see in the table. The standard OR gives a 1 output if any of the input is 1, but in the NOR gate, it gives 1 output when both inputs are 0. Next, we have here the exclusive OR gate, which is commonly called the XOR. This is the symbol just like an OR gate, except it has an additional curved line out in front of it, which makes it an exclusive OR gate. So it takes 2 or more inputs, gives an output which is the Q. Algebraically, the symbol for the exclusive OR gate just look like A or B, A plus B, but there's a circle around the plus sign. So in our truth table, looks very similar to the OR gate, except that when both input signals are the same, you'll get a 0 output. So only when 1 or any other input is 1, then you'll get a positive output. So just wrapping up, we've covered the NAND gate, NOR gate, and the exclusive OR gate.
What is digital circuits design and its application? It is a branch of electronics which deals with digital signals to perform the various tasks to meet various requirements. So, digital circuit is designed by using a number of logic gates on a single integrated circuit IC. So, for logical truth table, is a mathematical representation of the performance of digital signal when passed through the digital circuit. Logic gate is an electronic component that is implemented using a Boolean function. So there are different types of logical gates. They are AND, OR, NOT, NA, NOR, SOR, among which AND or NOT are the basic gates and NOD and NOR are the universal gate. So for now, I'm going to represent how design logic circuits from Boolean expression using basic logic gate. So we have to arrange the number of digital logic gates to the final output. So first, we have to identify this. So y equals a base plus b base and c. So first, we have to identify. So a base nag-represent siya og NOT gate. Nya ang plus nag-represent of OR gate. Nya ang B nag-represent of AND gate. So for NOT gate kay mao ni iyang design or symbol. Circle niya. So sa OR gate kay mao ni. And the last is AND gate. So this these are the symbol or design sa NOT gate or gate and gate. So ini sila kay nabilong ni sila sa basic logic gates. So for A, B, and C, so we're going to represent. So design or symbol sa A base kay kanina. Same with B. So kay A plus B ato man siyang A plus, so mauni ang yes. So ato i-kuan diri ang A base nya ari ang B base. So kay A base plus B base man, so ari siya naton i-kuan. So for C, inana siya. So ari siya nato i-kuan. A base plus B, A base plus B base plus open parenthesis and C equals Y. So this is the final output of basic logic gates. Thank you.
Simplifying logic expression using Boolean identity. The most practical use of Boolean algebra is to simplify the logic circuits. The number of terms and operation in a Boolean expression is directly related to the number of logic components. Through Boolean algebra simplification, a Boolean expression is translated to another form with less number of terms and operations. A logic circuit for the simplified Boolean expression performs the identical functions with fewer logic components as compared to its original form. Additionally, the simplified Boolean expression when implemented to a logic circuit is reliable with a reduced cost. For simplifying the logic expression using Boolean identity, we have to apply a series of Boolean algebra laws and rules. These Boolean algebra laws and rules includes the OR rule, the AND rule, the absorptive law, distributive law, associative law, De Morgan's theorem, double negation law, commutative law, complement law, annulment law, and identity law.
So let's take a look at some of the rules of Boolean algebra. Variables in Boolean algebra can only have two values. First, binary 1 for high, and second, binary 0 for low. Complement of a variable is represented by an overbar. Their complement is opposite. The complement of 1 will be 0 and the 0 will be 1. Logical or operation is represented by a plus between variables. Example, A plus B. So we read it as A or B. Logical AND operation is represented by a dot between variables. Example, A dot B. We read it as A and B.
So now I will be showing you a couple of examples in simplifying logic expression using Boolean algebra. In simplifying logic expressions, we need to base it on the Boolean algebra laws and rules. There's a lot of laws and rules in simplifying, but here I will only use the basic or common rules that is used in simplifying. These are the AND rule, gate rule, and the OR gate rule. Another common rule is the absorption rule, which we'll be using later for the example. Okay, so let's take this as an example. Simplify z equals to a bar b bar c bar plus a bar b bar c plus a bar c bar. First step to simplify this expression is to identify the common terms. So we can see that a bar b bar is common here in the first term and the second. So let's write it down. A bar b bar rounded into c bar plus c bar plus c plus a bar c bar. So here we can see c bar plus c. We can apply the OR rule gate here. This rule, a plus e bar equals 1, or vice versa, a bar plus a equals 1. So this will be equals to 1 as paired as the OR rule. A bar b bar multiplied by 1. So we'll have a bar b bar plus a bar c bar. So if there's no further simplification possible, we can now say that this is the simplified expression to this. So this is now the final expression. Here another example. Simplify z equals ab plus abc plus a bar b plus a b bar c. Again, let's identify what are the common terms in here. We have AB and AB here as common terms. Let's put it down. AB 1 plus C plus A bar B plus AB bar C. So here I put 1 because of the OR rule gate, which says that any value added by 1 is equals to 1, or vice versa, 1 plus any value is equals always to 1. So a 1 plus c is equals to 1, and 1 multiplied to 1 is equals to ab, and plus a bar b plus this a b bar c. Now let's find the common terms again. Here we can see b is the common term, so let's put b rounded into a plus a bar plus a b bar c. So diri nga part sa a plus a bar, naka-apply kita sang OR rule gate, which says that any Boolean value added to any complementary value is always equals to 1. So this will now become 1, and b multiplied by 1 is equals to b plus a b bar c. So in this part, we can also apply another common rule, which is the absorption rule, which says e plus a bar b is equals to a plus b, or simply remove the a bar to get a plus b. So let's write it this way: b plus b bar. Giuna na ko utang ang b bar to make it look like the absorption rule. Here, now na ang b bar, a bar I mean, added into AC. So again, nahimo ni siyang b plus b bar added into AC. It's because of the absorption rule nga gi-apply. So this will now become b plus AC. Kaya gi-remove naman ang b as paired to the absorption rule. A plus a bar b is equals to AB. This is now the final simplified expression of this expression. Or we can write it this way into an alphabetical order, which is A, C plus B.